Thank you very, very much. Nice to meet you again via internet. I see there are 18 participants. Thank you very much for the interest. What I'm going to present is a research that I had done both at Purdue University and at UCLA. This is the research that was done over 20 years. And my professor, Bhuani Roy Chaudhary, was helpful in this whole research process. The world has come to a point where there is a huge number of devices, and we need to have a good way to do machine learning at the edge. Okay, so what I'm going to do, if I share my whole desktop, I don't know if the view will be big enough because I need to show the Docker window as well as the slides. So this is where I will show my slides. This is my Docker desktop. But what I will do is once the Docker is started, I'm going to go ahead and switch out of the whole desktop mode to just the slide mode. Okay. So there are a couple of files I would like to distribute. One is this file, and I would like to send it out to the chat window here. Please open this file. Anybody who is on the chat window will be able to open this file, and it has instructions that I'm going to go through. A curious point for me is this whole thing is a hands-on workshop, and therefore I would need a Python Jupyter notebook. A matter of interest for me is how many of you do have the Jupyter notebook already started, but more importantly, are there people here who do not have the Jupyter notebook started? Put it in the chat window and I'll be able to see it. Okay. Anyone needs help setting up the Jupyter notebook? Oh, you're listening in iPhone, that will not work. Okay, so I'll count that out. Is there anybody else who is on a desktop and does not have the Jupyter notebook? Please raise your hand. If you do, then I would go through this exercise. Otherwise, I will jump in straight into the presentation. Okay. So no one has everybody has Jupyter notebook? Okay, I do a very brief one for Jupyter notebook because I do have to set up myself. I was basically going to go through this directly. So before I start the presentation, I want to, this document basically gives you the setup for Jupyter notebook. So the steps are, you need to have 25 gigabytes free on your desktop. I'm on a Mac. So download the appropriate Docker, and I have already done that, and I have started the Docker. And if you have a notebook started, you can just simply click play and the notebook will start. Drag Docker into the application, open the terminal, install the Docker, and it will be available. Okay, so the way to start the Docker is to go in the Jupyter notebook is to type in the Docker images. Okay, in a terminal window. So if you type in, sorry, one second. I pasted the wrong thing. Is it possible to this kind of workshop can anyone do on Metaverse? Yes, you could, but so you do the Docker images, and there is an image ID here. Okay, so this is the image ID. You copy the image ID, and you type in the this particular stuff here. Okay, and then you put in the image ID after that. Okay, if you put in the image ID, that basically starts up a Jupyter lab.
One second, Chanchal.
Yes.
Tom, you raised your hand. Do you have anything to ask? You can post the question in the chat if you want. Go ahead, Chanchal. If he has, he can post it.
Okay, so basically I skipped the steps of downloading the Docker and so on and so forth. So what I'm going to do next is I'm going to bring in, maybe I can do it right here. I can type in localhost 1234, and then this screen comes up. 1 second, let's remove this out of the way. Okay, and this is a token right here that showed up. Okay, and you click in the token here. I'm going through these steps very rapidly. I did share the document at the top here. Somebody's asking if I shared the document. Do you not have the Jupyter Lab? This particular person, Aravindan?
Yeah, can you post it to everyone? I'm not sure. Do you want me to post the setup link which you have sent, right?
Yeah, this one, this particular doc. It's a Google Doc. So anybody can open. Anybody who click, I posted again. Now this is shared with anyone with the link. Anyone at the link can be a viewer, so you can view it. I'll see if that is, okay, sorry, that other link may not open. So let's delete this and just keep this. Okay.
We didn't get it in chat.
I did place it in chat. Do you see my screen?
Oh, okay. Are you posting in webinar chat or your?
In the webinar chat.
Oh, we didn't get it.
What is there any other chat? So when I click here and I click.
Can you send me an email or else I'll post it?
Okay, 1 second. But this chat window has to work for me. It is important.
Yeah, it's working, but I'm not sure. I got your message.
You got this link? Can you click on that link? Lena?
Oh, no link.
No, this one, http://docs.google.com.
Yeah, we are not getting any messages from you.
Why is that? I'm in the webinar chat. See, you can see these messages, right? Can you see my screen? Okay, yes, maybe. Okay. I think it is. I'll do it, everyone. Okay, that's the problem. Okay, did you see it now?
Yeah, you're able to see.
Okay, so what happened is that I had it in Global AI Conference. I don't know the difference between Global AI co-host. Okay, that's probably only going to Dr. Murthy. Okay, great. So Venkata, do you have the Jupyter Lab running? No. Are you on a desktop? Oh, you're just listening. Okay, so anybody else who is on a desktop who needs Jupyter Lab running? So I got my Jupyter Lab running here. Okay. So if you already have Jupyter Lab, if you don't have Jupyter Lab running, I'll still go through the exercise. I'm hoping that some of you do. Okay. So the Jupyter Lab has come up. One easy way I test is you can create a Python notebook, but I'm going to skip that step also. So I'm going to just clone the adaptive algorithms, okay? So I'm going to open a terminal window and I'm going to clone this and it's going to clone all the entire library, okay? So I'm going to delete this work because that's not my library. So this is the adaptive ML workshop algorithms. It's all coming up. Okay, so now it's done. All the chapters are there. The MATLAB simulations can be deleted. The proofs of convergence or PDF can be deleted. Okay. Okay. Don't worry, you can leave it there. What it is saying is that you have to go through file by file delete, and then you have to delete the directory. Or you can go remove -R. Oh, this is too much. Okay. So okay, that deleted the MATLAB also. Okay, now I would like to go to my slide deck. So is my screen visible?
Yes, Chanchal, it's visible.
Okay, so what I'm going to do is I'm going to skip through this. I'm just going to keep the chat window as big as possible so that I can hear people. I can listen to people's comments. Okay, so the topic of today's discussion is adaptive ML algorithms. Now that we have set up the Jupyter notebook, we are ready to run. Okay, this is a book that came out of extensive research we did at UCLA as well as at Purdue University. And it presents a whole bunch of very complex ML algorithms that can be done by simple adaptive steps. So the book is, this is the book, it's this is the Springer Verlag link to it. The book has over 10,000 downloads now. So it's been highly accepted, quite a bit accepted by the community. I'm very happy about that. Next is that there is a GitHub that comes with the book, and you can just quickly go to the GitHub and download it without buying the book. The book basically explains the algorithms that are described in the GitHub step by step. The GitHub is free. So why adaptive algorithms? Adaptive algorithms are critical when the data volume is large, data has high dimension, and data is time varying, and has changing underlying characteristics. And we do not have sufficient storage, compute bandwidth to process the data. Okay. So it's important to know that if you have very large dimensional data, I'll go to this slide show mode and I'll switch back and forth. When the data has very large volume, and like, for example, if you are doing shopping data, if you're purchasing like 20 different items, for each item, you'd have many dimensions of data, like the price, the time, the geolocation, the person, the type of credit card used, all of that, and what is the item. And sometimes those items have a skew, this, that. So you could easily end up with 100 or 200 dimensional data. The data also can be time varying, because what happens is that you have certain trends, certain seasonality characteristics, like very few purchases happen in the middle of the night. More purchases happen during Christmas time than other times of the year. So you have certain seasonality and time varying nature of the data. And also for a lot of items, you have an increasing demand or a decreasing demand and various types of changes in the demand. So it becomes very difficult to track the actual nature of the data. And the underlying statistics of the data also changes. These are all characteristics that happen to data in a real world situation. And we do not have sufficient storage, compute, and bandwidth to process the data with low latency. So, for example, if you take any country that doesn't, that has a billion phones, like let's say in India, we have like 600 million phones there, or edge devices. You cannot keep updating this high dimensional, high volume data to the cloud. You'll fill up storage like anybody's business, okay? So you need to process the data locally. And the local phones may not be that powerful. They're not buying iPhones in the quantities that we buy here. So most of the phones are low-end phones. And therefore, you don't have sufficient storage, you don't have sufficient compute, you don't have enough bandwidth. Bandwidth is also irregular. In geographic location, metropolis may have good bandwidth. If you go slightly outside, you lose bandwidth. That happens here too. And then you also need to process the data with low latency, which means that if you want to give a recommendation to somebody buying a product at a store on their phone, you want to do it right away, right? If you're using the phone app to do the payment system is pretty good in India, for example. You are paying in China too. You're making payments on the spot with your iPhone, with your phone, and then you want to see an ad, a coupon or something like that. So edge devices and computation is an example of that. So I premised this whole book on the edge device and edge computation reason as the main use case. You can have many other use cases, but this one I thought would be the most useful, most potent, and the most valuable. Due to the rapid proliferation of billions of devices at the cellular age and the exponential growth of machine learning and analytics applications on these devices, we have an urgent need to manage the following: power usage, the non-stationarity of inputs, latency, and memories and bandwidth of devices. So we want to basically, we need to manage, we need to do all the computation without running out of power, and we need to handle non-stationary data. We need to do this at low latencies, and we need to do it at the small memory and bandwidth requirements. In these environments, we have certain constraints. Data cannot be batched. You can do mini batches, small batches of 10 or 20, but you won't be able to take thousands of samples and batch them together and do a batch training, okay, like back propagation. Need to be used instantaneously. The data comes in, you have very little storage, you don't have enough power, you have very little memory, okay, and you want low latency, so you cannot batch it for an hour, then the latency is gone. The data comes in 1 per millisecond, you want to get that data processed, and you want to get the update. We have a streaming sequence of vectors or matrices as inputs to these algorithms. The data changes with time, which means data is non-stationary, and the data volume and dimensionality is large. So we cannot batch the data. We have to deal with time varying data, and the data volume and dimensionality is large. So I'm trying to form the premise why we wrote the book. Does anybody have questions? Okay, no problem. Okay, moving to the next slide. So we took several use cases. Calculate feature drift of incoming data. So for example, if you're doing training of data, you want to know training serving skew, adapt to incoming data drift and calculate features that best fit the data, calculate anomalies in incoming data, compress incoming data into features for use in new model creation. So instead of trying to keep building, transferring all the raw data up to the cloud, you want to have a compressed data that you are sending it out to the cloud so that you don't have to send a huge volume of data. So the matrix algebra functions that we compute adaptively are normalized mean, median, LU decomposition, which is square root and inverse square root, eigenvector, eigenvalue, which is known as PCA, generalized eigenvector, singular value decomposition, and generalized singular value decomposition. So these are some of the matrix functions that we compute. So basically, we take these real-world problems and we convert them into matrix algebra problems. And then we find an efficient algorithm to compute those matrix functions. So those are the 3 steps that we follow in this book. So take a real world problem, like calculate feature drift, or calculate incoming data drift, or calculate anomalies, compress the data. Compress the data can be easily converted into eigenvector decomposition or eigenvalue projection, eigenvector projection. And then we compress so then we find an adaptive algorithm for eigenvector. So that's the idea of this dissertation. So why do we need adaptive algorithms? The reason we need adaptive algorithms is because we have, because these adaptive algorithms arise due to edge computation, which require managing like power usage of device, computation at scale, non-stationarity input, latency, and memory and bandwidth. These are points I already made. In all these cases, we have the constraint that our data arises as a sequence of vectors, xk, or matrices, ak. Our data changes with time, causing significant drift of features. The data volume is large, which means the dimensionality of xk or ak is very high. And data volume can be large too, which means that the k changes, k to k plus 1 to k plus 2 happens very rapidly, maybe in millisecond scale. Okay? So it looks like there is a new question. Okay.
No questions, Chanchal.
No question. Okay. So I have set up this agenda for 2 hours and I have crossed out certain items which I thought we won't be able to fit in this time. So set up the notebook is something I did or skipped very rapidly. Then introduction, general theories and notations, first principle eigenvector, principal and minor eigenvector, generalized eigenvectors, and real world applications. Okay, so let's skip this, set up the notebook and go to introduction. And now I will need to get on the, okay. So here's a good example. You have a high volume, high dimensional data. I'm just showing 2 dimensions of the data. So you have a distribution of data here and a distribution. Let's say it is 2 components, but it could be a 100-dimensional or 200-dimensional data, the same theory applies. For visual purposes, I have taken two dimensions. So the vector E1 that I have shown is the best to represent the data, which means that if you take this class and you project it onto this vector, or take this class and you project it onto this vector, then you would get the best representation of the data. As you can see, this data has very little value in the dimension that is perpendicular to U1 because most of the values are concentrated along this axis. Okay, so if you did an eigenvector decomposition, you'd see a very large eigenvalue in this direction and very low in this direction, and there will be two eigenvectors. So if you project this data onto this vector and reduce this two-dimensional data to one dimension, which is 50% reduction in size, you will still capture almost all the characteristics of the data. Okay. Whereas if you want to classify these two, then if you project the data along this axis, which is completely perpendicular to this, orthogonal, and you project all the samples to this, it will form a mass along this line, this section, and it will form a mass along this section, and you'll be able to neatly classify it because now you have taken the two-dimensional data, converted them to set of points here and set of points here, and you take a line and it will neatly divide this cluster and this cluster. Okay, you don't have to take a two-dimension or 100-dimensional clustering problem. You can just project it onto this, and this two-dimensional clustering problem becomes a one-dimensional clustering cluster, and then you can easily separate, just pick a point in between, and that's the classification of class 1 and class 2. Okay, so this picture is shown with the whole idea that in order to represent the data, the features that you create for data representation are different from the features that you need to create for classification. Okay, so the representation features, if you take representation features and use that for classification, you may not be doing the right thing. Similarly, if you take the classification features and you, in a multi-class problem, and you take that as a representation features to represent the data, you will also do a poor job of features. Okay, so it is important to understand. So all these large language models, the attention networks, this and that, are all based on how to do a proper extraction or how to do training in order to learn the appropriate tokens that are useful for identifying languages. So the extraction of the features there, they are very clearly identifying the data representation features. So going to another class of problems. So this is where I wanted to show what the data representation and classification are two separate problems. Next one is what is called the whitening of the data, or basically take a very noisy distribution of data. Here is the distribution of data in two-dimensional space. Very, very uniform distribution with one bright spot here, but mostly uniform distribution. But data whitening is a process, okay? This is a correlated data. You won't be able to separate one dimension from the other, okay? So basically this data, if you take only one dimension, you will underrepresent the data. If you take this dimension, you will underrepresent the data. But if you transform the data with a whitening transform, then this same data becomes a diagonal set of points. So if you take the points along this axis, then this is all the information in this whole two-dimensional correlated data becomes uncorrelated. Each axis becomes different. Each component becomes separate. So you take 100-dimensional data, highly correlated, okay? Like the price with the volume might be highly correlated. sales volume might be highly correlated. But after you do this transformation, you'll get a new set of features which will be uncorrelated from each other. And the advantage of uncorrelated features is you can take each feature and based on which you can create statistics, you can do projections and stuff like that. Okay, so this is basically converting a correlated data to uncorrelated data. The next one is principal component analysis. This is again a two-dimensional data. I've drawn these visual pictures to give you an idea of what happens in these situations and why these are important transforms. You have a very correlated data in two-dimensional space. Then after you project it into the two eigenvectors, you get neat points. This particular point is most important. This is less, this is less. And as you can see, after fourth feature, everything else is unimportant. So here are 10 features, which you can reduce it to 4, which is basically a 40% of the total data volume. That's a 60% reduction in data volume. So if you have a terabyte of data that has been collected at the edge, you can easily reduce it to 400 megabytes or something, 400 gigabytes or something like that. And you can do even more and reduce it to 10%. Okay, so this, if you just took this one feature, then you'll mostly represent most of the data. Okay, so this is what the principal component is all about. This is used highly in data compression. It's a very powerful feature in data representation to represent the data. And this is what the autoregressive models do. Autoregressive model in a nonlinear space basically extract the principal component features in the latent space and then use that for the for projection. So basically it has a encoder and decoder. Encoder is basically a principal component analysis, and the decoder is just the opposite. Okay, so same with the attention network. You have the encoder space, the large language models, you have the encoder, and then you have the decoder. Okay, so that's why this is very important to have a transform like this. So the next one, but I want to pause a little bit and make sure that everybody's listening. Can somebody give me a ping or a thumbs up that you guys are there? I don't know how many people are still there. How many people are there, Lena?
We have around 15 plus.
How many?
15 plus. 15 plus.
15 plus. Okay, so we have almost everybody. Okay, I don't have a way to see how many people are there. Awesome. So you guys, can you give me some feedback whether you like this mode of presentation or do you want me to change? I can go to coding also. So Aravindan said thumbs up. Anybody else wants to give a thumbs up or thumbs down? If it's a thumbs down, I'd like to have the suggestion as to if there is anything I could do that is better. Okay. This is very good. Okay, thank you, thank you. So the last feature, so I wanted to, here I took the example of representation versus classification. Here I gave you a good example of uncorrelating of the data. Here I gave you an example of representation of the data. Now I want to give you an example of linear discriminant analysis. Linear discriminant analysis is another statistical technique that is used for feature extraction. And when you take a very nonlinear network like convolutional neural network or autoregressive or any of these networks, then autoencoders, then they basically fundamentally do these transforms in a nonlinear space. Okay, It's mathematically can be proven. So linear discriminant, if you take an autoencoder in which you do an encoder and the next stage is instead of a decoder, you do a classifier. If you connect a nonlinear network, a very high dimensional data, convert, let's say 1,000 dimensional data, convert it to 50 dimension, and then you do a classification into 5 classes. You will see internally, it will do a linear discriminant transform in the latent layer, in the latent vectors, and then it will use that for classification. Now, if you do autoencoder, in which you will take the 100-dimensional data and you convert it to 50 dimension and you project it back to 100, it will do this principal component analysis internally. Okay, linear discriminant analysis, this is highly correlated to dimensional data. It's very easy, hard to know which data is from which class. But after you do the linear discriminant analysis, you will see that there are 2 underlying classes in the data. So the data can be easily clustered after linear discriminant analysis into 2 clean classes. Okay, so linear discriminant analysis is basically generalized eigenvector. Principal component is an eigenvector. This is basically a square root or an LU decomposition in matrix terms. Okay, so I wanted to take these 3 examples, show that data representation is different from classification. Data representation feature is different from classification feature. In this case, they're completely orthogonal. This one shows that we can uncorrelate the data very easily. This one shows that we can represent the data with principal component analysis. This one shows that we can classify the data by extracting linear discriminant analysis features. Okay, so why adaptive algorithms? First, the dimension of the samples may be large, so that even if all the samples are available, performing the matrix algebra may be difficult. So let's say you have 1,000 dimensional incoming samples, and you have 1 million samples coming in per hour. So you have a 1,000 by 1,000 size matrix. And if you take a 1,000 by 1,000 matrix, then the computation, the eigenvector computation is ordered in cube, which is 10 to the power of 9. So if you take a tiny little cell phone, okay, on the field to do a principal component analysis of a 10 to the power of 9 order matrix, it's very difficult. Okay, and if these are computations you can do on the cloud or in the data center. And the phones are not sophisticated enough, and even if you have the power, the compute power, if you do that computation, your battery will go down to 0 in 1 hour. So all your algorithms is going to exhaust the battery, and the person will say, why am I, where's my talk time? Okay. Second, the matrix functions evaluated by conventional scheme cannot adapt to small changes. So let's say you come up with a sophisticated algorithm to take this data, micro batch it, and then find this eigenvector. Now you got a new sample, which is quite different from the previous one, because what happened is that you have data in the store, let's say in the morning, the demographics of people that come in, buys coffee and donuts and all that is different from the guys who come in the evening after work, who are basically buying bread and chicken and stuff for dinner. So the change, the underlying nature of the, let's say, this e-commerce data will change with time of the day, and you'll have to adapt to that. So if you do this high batching of the whole day, you will miss the micro signals that you get on an hour-to-hour basis. So you need to have an adaptive algorithm that will work on samples that are coming in now. Now is more important than what happened in the whole day. Okay, if the matrix functions are estimated by conventional schemes, method from k samples, then for each additional sample, all of the computation has to be repeated. Okay, so you microbatched it to thousands, batched it to 1,000 samples, you did this whole eigenvector computation. Then you got the next sample, you add that, and then you have to do this whole matrix computation again. You want to do the delta computation, not the whole matrix computation. So that's what this book is all about, how to do the delta computation rather than the entire matrix computation. Okay, so you want to handle large dimensions, you want to reduce computation, you want to capture the now, and you want to do the delta computation rather than the whole matrix computation. That's what these 4 points are about. So this is our approach. And our approach is very simple, that giving a streaming sample xk, let's say this is your purchase data, e-commerce data, we are going to come up with a simple update rule. The simple update rule will be of this format. This is, let's say, the eigenvector. I compute it from k samples. Then the next sample as it comes in, I'm not going to do a whole matrix computation. I'm going to, which takes order n cubed, which is 10 to the power of 9. I'm just going to basically use a simple matrix vector multiplication rule, which will be order n multiplication, okay, simple multiplication. That will give me the next eigenvector. It is not the accurate value of the next eigenvector, but it is close, okay? So I'll update the next value based on the previous value and some simple function, okay? Simple function that will include the old eigenvector and the new sample, okay? So this can be for eigenvector, for linear discriminant analysis, singular value decomposition, any of these matrix functions. We are going to use this simple rule in order to update. So for case of eigenvector, we have an eigenvector now. We'll use this simple function and calculate the new eigenvector. Okay, this is the last value of the feature. This is the new value of the feature. This is the newest sample. This is a simple matrix, a simple vector multiplication. Okay, so this is the famous algorithm which was invented by a person called Oya almost 30 years ago for eigenvectors, saying that if your current eigenvector is wk at time k, then you can get the next eigenvector from the samples by doing this simple multiplication, this order n multiplication. These are all order n multiplications. So basically, you get an order n computation. So if you have 1,000 dimensional data, you do 1,000 matrix multiplications rather than million matrix multiplications or 1,000 million matrix or a billion multiplications. So you have reduced the order of computation significantly down by 10 to the power of 6, almost, okay, by n square in order to get the result in n, okay, in order n rather than order n cubed. Okay. So this is an e-commerce. I keep giving you the example of the e-commerce. Okay, and I have the code for it, and I will show you. So, so the chapter 1, if you go to chapter 1, which is the introduction, I have the auto association example, e-shopping sentiment analysis. Okay, Hebbian example, heteroassociative, which is basically linear discriminant analysis, principal components example, data whitening example. I have all these, okay? I can cover all of these, but I'm setting up the stage so that you guys can download this code and you can try it yourself. So for example, if I click on the e-commerce, so here we have data. I collected public open source data. This is UCI clickstream data. So e-shopping clothing from 2008. This consists of data which is order, country, main category, color, location, model, photography, price, different prices and pages. Okay. So if you look at the different components of the data, the order is varying like this. The country is more or less same. It's probably between US and Canada, so you only see mostly US and one or two others. Main category is almost same. There's a lot of variations in between, but since this is almost 20,000 samples, you don't see the variations in between. Excuse me. So we compute the eigenvector in a very rigorous way. So you take the entire sample of data, the entire corpus of data, okay, whole data set, and you transform it, okay, and then you basically take XX transform. Let's say you have 1 million samples, each of them constitute excuse me, of 100 dimensions. Is 100 by 100 divided by the number of samples, so you get the average correlation matrix. Then you compute the eigenvectors. So these are the eigenvectors. These are the eigenvalues. You see, the first eigenvalue is like 2,922, almost 3,000. Second eigenvalue is 185. So see, the eigenvalues are dropping in value significantly. 3,000, 185. Okay, and then 84, 19, 3, 1.5, 7, this is 0.7, 0.3, 0.15. So clearly, the first one is 3,000 and this one is only 3. So the importance of these 1, 2, 3, 4, 5 vectors, 5 eigenvalues is much less compared to the first 4. And you can even ignore some of them. So let's say you take, so these are the eigenvalues. So this is from a data compression perspective. You can see only the first 4 eigenvectors are important, the rest are not. Okay. So you take an adaptive algorithm. This is an adaptive algorithm that we created. You use this adaptive algorithm and you compute the eigenvector, okay? And once you see in Python, it doesn't show it very well, but this is a 10 dimension by 10 dimensional vector matrix. So now what we do, we take the actual eigenvector, okay? And we show you how this eigenvector that is computed adaptively, how it converges to the actual eigenvector. So the actual eigenvector was computed here in this code, okay? And here we are computing adaptively sample by sample. As the sample comes in, we compute it. So the actual eigenvector where we batched 1 million samples and we did that. But this one, we are computing sample by sample. So you'd think that computing sample by sample will get very inaccurate result. But this curve shows that the first principal eigenvector converged almost within 50 samples to the true eigenvectors. This is the dot product of the true eigenvector with the computed eigenvector and converged very, very quickly. The second component converts in like 500 samples. So basically what I'm saying is that as the data is coming in batch, you don't have to take the whole sample and do a billion multiplications to compute it. Here, we are doing a simple vector matrix multiplication, and in 100, 500 samples, we are getting the first 2 or 3 eigenvectors very, very accurately. So this is the first one is the first sentiment, second one is the second sentiment. And so here is an example of all the different features, which was very, very highly distributed. From there, we could get very, very clean eigenvectors out of it. This is the code. So this is the actual eigenvector. This is what we computed with the adaptive algorithm. And this is the basically projection of the adaptive eigenvector sample by sample with the actual eigenvector. Okay. Any questions? Okay, so here's the e-shopping clickstream data that I showed. We have 1 more hour. Let me finish this chapter and then I will take a short break and then we can move on to the next chapter. Okay, so what are the advantages? So conventional solutions find all eigenvectors and eigenvalues, whereas the adaptive computation only finds the significant eigenvectors and eigenvalues. You don't have to find all of them. Okay, so if you do a whole matrix multiplication, you'll find all of them. So you saw in that example, you had 4 that were important, and the other 4, these 4 are important, and these 4 are completely worthless, very, very small compared to them. So why compute all 8? Why not just compute 4? Okay, so that's the first. The computational computation is very, very low. It is only order n. Adaptive algorithms easily fit the framework of time-varying data. So if the data is time-varying, then your eigenvector will keep changing, and this will adaptively compute that. What are the disadvantages? The adaptive algorithm produces an approximate value. As you can see, it was not the correct value for at least 400 or 500 samples till it converged. Okay, this is good when you have billions of samples. The adaptive approach requires a ramp-up time to reach the accuracy as evidenced by the curves. Okay, so there is a ramp-up time. So that's basically the disadvantage. Okay. So how do you derive this algorithm? This is one slide that tells you, the book has given examples of a few matrix examples, but you can extend it to other examples. Like if you take large language models, so this book was written before these models has happened. If you want to take an attention network and also create an adaptive version of it, how would you do that? Okay, you basically create an objective function that you're minimizing, right? If you take the adaptive network, then you are minimizing an objective function, right? If you read that paper, attention is all you need, then you'll see there is a specific objective function that you're minimizing. So you take the objective function and you use the gradient descent rule to approximate it. Okay, so that will be very helpful to find out what is the objective function that they're minimizing. So in convolution neural network, they might minimize error and all of that. So here you can take that objective function and you can minimize that. So then you can also find methods that are well-known methods like Newton-Raphson method, accelerated gradient, conjugate direction, steepest descent, Newton-Raphson, recursive least squares. You can apply optimization theory techniques to this simple algorithm to make it better. There is a whole chapter in the book to deal with that. We obviously won't have time to cover that. It has been highly quoted. That particular chapter is still being quoted by a lot of people, even though it was written almost 15 years ago. We'll show that these algorithms converge to the matrix function. So basically, you need to start from an objective function, create a gradient descent approximation of it. You can speed it up by certain methods of optimization theory, like steepest descent, conjugate direction, Newton-Raphson, recursive least squares. And then you show that these algorithms converge efficiently. Okay. So now, 1 second. So what are the matrix functions that will compute? So like I said, you take a real world problem, then you convert it into a matrix function. Then you use a adaptive version of the metric function. These are the 3 steps. So mean square and correlation, median, mean, and correlation. Then you can have square root, principal component, principal and minor eigenvectors, generalized eigenvectors, acceleration, and singular value decomposition. These are the various chapters of the book. This is the GitHub. Okay. With that, I'd like you to take 10 minutes and ask some questions, and we'll convene around 4:30. And then we can continue the rest of the presentation till 5:20. Okay.
Okay.
So I'll just go on mute and see if people have questions or they want to take a break for 10 minutes. We'll reconvene around 4:30. Okay. Thank you, Lena.
Yeah,
how many
sure.
people do you have still? We have 16. Oh, that's very good. Not bad.
Yeah, we are back from the short break. You can
Yeah.
continue, Chanchal.
Yeah. So, Lina, you're saying we should get do a quick demo. Is that right?
Yeah, theory and demo should be fine.
What is that? Theory and demo. Okay.
Yeah, yeah.
Okay. So demo means going through the code, right?
Yes.
Okay. So here's a good example of doing a demo. So how to do adaptive anomaly detection. So your data changes like this, and you want to quickly do an anomaly detection. And if you have a data center, you can run some very sophisticated algorithms to do anomaly detection. There is a public paper I wrote on data center anomaly detection by using a algorithm from Google called MADI. When I worked at Google, we used that. It's multidimensional anomaly detection with interpretation. That's an awesome algorithm, but it requires a lot of computation. It makes up to 2,000 models. But when you are on a little device, then you cannot do that. Okay, so let's go to the code. Okay, so anomaly detection. Okay, I think it's in the experiment section. So this is the anomaly detection example. So this is the data. We got real data from a source. I think I mentioned it in the book. I can't remember. Yeah, Yahoo Research Web Scope data. Okay. So there, what we did is we took a certain number of dimensions, like 8 dimensions, 1, 2, 3, 4, 5, 6, 7, 8 dimensions of the data. And then you see this is normal data, then you have spikes, normal data and spikes. So one good technique is to constantly compute the median in an adaptive way and take the difference of the current sample from the median. If the current sample deviates from the median by over 2 medians, then you can say that's an anomalous sample. You can come up with a heuristic algorithm like that. So the medians of the entire data, if you take from the whole data and you compute it like this, the median computation, then you find these are the medians. But this is the adaptive method of computing the median. So the adaptive method of computing the median, you start from 0, you take the first sample to be 0. And then for every iteration, you just take the sign of the current sample minus the previous median computation. Okay, so that's the algorithm. So once you do that, and I have a section describing that, and then once you do that, then if you say if the difference of the current sample from the current estimated median is over half the median, that is, you take the current sample minus the median, and it is almost another half a median higher, that means it's anomalous. So we did that algorithm sample by sample, and we plotted it whenever we found. This is the green line is the median, adaptive median computation. The red dots are when we found the median. Okay, whenever this value was higher, it clicked a point and we got these red dots. Okay, so that's a great example of an adaptive anomaly detection algorithm. Okay, so I have a whole bunch of other algorithms to cover like that, but I just wanted to give you a quick summary of that. The other is character recognition, adaptive mean handwritten character recognition. This is a very complex problem to solve. This is solved by deep learning, convolutional neural networks. Even then, they get only 80–85% accurate. So you take the character, you take various different handwritings of it. So one simple algorithm would be to find a template that represents this algorithm, this character, okay? Like this character has certain extra features, this character has certain extra, there's certain extra, but there is a common mean. So you compute the adaptive mean, okay, by an adaptive algorithm, and you get a mean like this, where you'd see that all the samples have the center part common. See, that's the highest density there. The top portion is also very good. The bottom portion is good. There is not enough correlation on the left edge because each one is slightly different. You can see this is small, this is large. Even the top edge is not all that good because some are slanted right, some are straight, so on and so forth. But certain parts like the center is good, the bottom is good, the top is good, the right side is good. And you do what is called an adaptive mean algorithm, okay? And then you can, I have that, some chapter, I have to see where it is. Oh, right here, mean. Okay. Oh, there is the anomaly detection. Okay, so mean of the MNIST data. So this is the MNIST character 8. See how many variations of 8 there is. Okay, see how the bottom part keeps changing for each of them, but the intersection in the middle is common. Okay. So you take the character and you come up with the mean algorithm, which is equation 2.4 given in chapter 2. Okay. And then you basically use this algorithm to compute the mean. And you find if the mean is, you use that mean in order to determine the character. Okay. So here's the mean that is computed. Here's a three-dimensional view of the mean. And you can use this and you can correlate that with character by character. And then you can see if you get a good correlation. So a long time ago, before OCR was done by deep learning, there was another problem where you had inkjet characters, that is the date and lot code that is printed on a lot of these bottles. They vary in slight shape. These are not printed characters. Handwritten characters, a similar problem, is quite a bit of variation. So finding the mean and correlation to solve this problem is certainly a main issue that can be solved by this type of simple algorithm. Okay, so you can run this code step by step. I'm not going to waste time doing that. So next one, I'm going to talk about square root. I'm going to skip, and then we can go to principal eigenvector. So the principal eigenvector is a very interesting problem and a very useful problem to solve. So you have these, each of these are different samples. I just plotted them, stacked them one on top of each other, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10-dimensional data. So dimension 1 looks like this, dimension 2 looks like this, dimension 3 looks like this, dimension 4 looks like this. So the data was looking like this in all these dimensions. So our algorithm quickly converged to the principal component here. But suddenly at this point, we had an abrupt change in the character. You can see that this data, instead of being very low amplitude, suddenly became very high amplitude, this particular component. This component from high amplitude dropped to low. This is from one pattern of the low amplitude to another pattern. So 1, 2, 3, 4 components, and the fifth one changed drastically. So as this component, this one changed too. So almost 5 of the components changed. So the algorithm's principal component, and I'm also calculating the exact principal component by the traditional method, okay? By batching the samples, I'm calculating the principal component. So I'm taking the principal component that is computed by the adaptive algorithm and correlating it with the principal component that is computed from the exact value of batching samples and huge amount of computation. And I see that I converge very quickly to the actual principal component all the way up to very, very quickly and stay there till the data suddenly changes. This is the nature of the non-stationary data. So now all of a sudden, my adaptive algorithms principal component becomes bad, but it quickly recovers back in like 50 samples or so, or 75 samples, it recovers back to the full number. There's a steep rise and recovers back. So the adaptive algorithms are less accurate, but not for very long, for a short period of time. So as the data changes, it adapts to the new data. But in order to do that, if accurately, you will require a huge amount of computation. You have to batch the data. You have to take a sliding window, batch the whole data, calculate the correlation, calculate the eigenvector, principal eigenvector, and keep doing that batch by batch by batch. And then over here, you'll get a slightly different value, and then the transition to the new eigenvector will come at this point. But I'm saying instead of doing all that computation, if you use a simple algorithm, then you will see that it converges very quickly. So experiments with real world non-stationary data. There are various types of non-stationary. One is gradual, there is abrupt, okay, there's linear. So there are various types of non-stationarity. And I'll give you a quick glimpse of the various algorithms, and I'm going to use this particular adaptation where WK plus 1 equals WK. This is the eigenvector, principal eigenvector. This is the previous value of the principal eigenvector, plus a very small constant times this function. There's a function due to the inventor called Zoo. Okay, so I'm going to go into the first eigenvector. Okay, so real data. So this is the real data. This is actually insects. This is incremental abrupt. Excuse me. Incremental abrupt data. That's the particular sample I took. I plotted many, many dimensions of that data. 33-dimensional data. You can see it abruptly changes, abruptly changes. These are all changing. Okay, so sometimes gradual changes, sometimes almost no change. So then I take the whole data sample, I calculate the correlation matrix of the 80,000 or 100,000 data values, and I calculate the eigenvectors. These are the eigenvalues. You can see the first one is 18.7, the second one is 10.4, the third one is 9, 7.8, 7.2, 6.6, 5.5, 4.8. So it precipitously dropped after this value, it becomes 0.9 and so on and so forth. So if you want, you could take these 3 rows of values, which is 4 times 12, 4 times 3 is 12, 12 values out of 33, which is a 1/3 reduction in the data. So but we are only computing the first principal value, which is 18. The eigenvalue is 18, and the vector is corresponding to that. We took many algorithms, okay, to do that. Many algorithms, adaptive algorithms, but the one that is significant is this. This book is more like a dissertation, so it takes many algorithms and it shows the relative benefits of each. The book talks about the accuracy versus computation trade-off of each of these algorithms. And you can see all these algorithms converge pretty fast. This is OS algorithm. This is some of them, even though, so this is the least computation. This is the most computation. And you can see the least computation one also converges very, very fast to the true eigenvalue. Okay. So that was if you batch the whole eigenvalue and you compare it against them, it does very well. Now, I also have another one which is simulated data like this. And then I take the principal eigenvalues. You can see this algorithm converges very, very well. This algorithm also so you can see the simplest one is pretty good in terms of trade-off. So that's basically it. I need to send a response quickly. I'll be back in 1 minute. If you want, you can take this code and take a look at it. Okay, so this is the principal eigenvector computation technique that is discussed in the book. Next, I want to talk about principal and minor eigenvectors and how to use that for multiple different applications. One of the biggest application is data compression. So example one, I think the practical examples were taken up later on. Sorry, those are all the data. Okay, so here's an example of a high dimensional data, which is there in chapter 8 actually. So you can see that this is the data that has many components. Okay, we took 10 components because you cannot put 1,000 component in a book or paper, and we took 14,000 samples. And each component is quite different. Okay, I took features 0, 1, 2, 3, 4. Each component is like that. Okay, then I took the eigenvectors and eigenvalues, and I see the eigenvalues. First one is 68, 19, 7, and it drops. After this, it particularly becomes sub 1. Okay, so again, here you could probably take 1, 2, 3, 6 or 12 of the eigenvalues, and you'll get pretty good results. So we use the adaptive algorithm, okay, which is the zoo algorithm we used in order to calculate the adaptive eigenvector. And then we only took 16 samples out of what is the total? Oh, sorry, this data has 128 dimensional data. 128. I have only shown 10 of them, but this is the 128 dimensional data. So we took only 16 dimensions of it. So this data has 14,000 samples and 128 dimensions. And this data was obtained from gas sensor.csv, also from the same source that we got the data from, this one, USPDS repository. okay, google.com, USPDS repository. So we have 128 dimensional data, and we only computed 16 dimensions of it through the adaptive algorithm. And using the 16 dimensions, we showed the 16, I showed examples of how this converged in the first 4 eigenvectors, okay? And then I reconstructed the data adaptively, sample by sample. And this is the original and this is the reconstructed. You can see it visually, how it looks. Okay. So this is the original, this is the reconstructed, original reconstructed. Like it missed that little, it created a little dent here, which is slight aberration. But look here, it captured these small little changes here, this tiny. You can see that the reconstruction is very, very accurate. And this is 16 dimension out of 128, which is like 8 times reduction. Okay, so we got 12.5% of the data. So you can see it reconstructed it very, very well from the adaptive eigenvectors. And this amazing result, I was myself very surprised how accurately the adaptive algorithm recaptured the images by using only 16 out of the 128 dimensions, 16 eigenvectors. So it basically reduced the data from 128 to 16. Okay. The chat window. Any questions?